I lost the speaker. Yeah.
Okay.
Hello.
Hi.
See you again. No, it was a really nice talk. So
thank you.
Very to hear about this first, security paper. So we will. Yeah, we are live. So we welcome a second talk by Hai. And it will be now about the security of another problem related to symbolic authenticity. So please go ahead.
Thank you. Good morning again. So now I'm gonna talk about symbolic authenticity. Again, this is joint work with Chris Lynch. So here's the outline. First, I'm gonna.
Do you need to share?
Do you see the presentation?
Oh,
the presentation.
Yeah.
Oh, sorry.
Share again the screen.
Sorry. Screen.
Yeah.
Okay. Sorry. So first, I'm gonna talk about some background, and then I'll talk about symbolic authenticity, and then after that, I'll talk about algorithm for checking symbolic authenticity. So authenticated encryption schemes are ways of encrypting messages which simultaneously assure the secrecy and authenticity of data. Authenticated encryption schemes can be constructed using various ways. For example, it can be constructed using tweakable block ciphers. It can also be constructed using encrypt and then MAC paradigm. So in this work, we only consider authenticated encryption schemes constructed using tweakable block ciphers. And we only consider the authenticity property. And as a first step, we consider authenticated encryption schemes that handle messages of fixed length. So first, what is a tweakable block cipher? Well, tweakable block ciphers extend traditional block ciphers by introducing tweaks. So in traditional block ciphers, each key leads to a different pseudorandom permutation. In other words, if you want to get a different pseudorandom permutation, you have to use a different key. Well, in tweakable block ciphers, we introduce another dimension called tweak. So now each combination of a key and a tweak leads to a different pseudorandom permutation. So in other words, if you want to get a different pseudorandom permutation, you can reuse the same key as long as you use a different tweak. So the tweak doesn't have to be secret. It just has to be different each time. So we can construct authenticated encryption schemes using tweakable block ciphers. And here's the basic idea. So you process each block using a tweakable block cipher, but of course, each time you use a different tweak. Now, in order to achieve authenticity, you need to attach a tag to the ciphertext message. And the tag is typically computed by taking the XOR of some plain text blocks or some ciphertext blocks, and then you feed the result of the XOR to a tweakable block cipher. We say that a ciphertext message is valid if some verification equation is satisfied. So just to show you a quick example, so here is an authenticated encryption scheme that handles two blocks. So M1 and M2 are two plain text blocks. We process them individually, and then in order to compute the tag, we take the XOR of C1 and C2, which are the two ciphertext blocks, and then we feed that into tweakable block cipher. So here's the definition of authenticity. Essentially, authenticity says that the adversary cannot forge any new valid ciphertext message, but the the adversary can get some help by interacting with the oracle or the honest party. So the adversary can send a plain text message to the oracle, and then the oracle can respond by sending back a valid ciphertext message. And this process can be repeated many times before the adversary tries to forge a new valid ciphertext message. So let me introduce the notations. So we have variables, constants, and functions. We use the convention that variables start with uppercase letters. So M denotes plain text blocks, and C denotes ciphertext blocks. TG denotes a tag, and TK denotes a tweak. We have some constants. So M of IJ denotes the JS block of the ICE plaintext message, and CIJ denotes the JS block of the ICE ciphertext message. And tag I denotes the tag of the ICE message. And the TKI denotes the tweak for processing the first block of the ICE message. But since we need to use a different tweak for each block, in order to get the tweak for processing the next block, we use a function called n, which returns the next tweak. And we have a shorthand. N to the I means apply n I times. So we have E and D for encryption and decryption. Both E and D takes two arguments. The first argument being the tweak, and the second argument being the message. So those are the notations. Now that I introduced the notations, I can explain the example that I showed you previously in more details. So so again, we have two blocks, M1 and M2. We process the first block using tweak TK and get ciphertext block C1. And we process the second plaintext block M1 using tweak N of TK and get C2. And the way we compute the tag is by taking the XOR of C1 and C2, and we process that by using tweak N squared of TK. And in order to verify if a message is valid, we check if this equation holds. So essentially, we just recompute the tag and compare what we computed with what is attached to the message. And this particular scheme doesn't satisfy authenticity because if the adversary is given a valid message, so TK1, C11, C12, and tag1, then the adversary can forge a new valid message. And the idea is the adversary can reuse the tag and reuse the tweak, but the adversary can modify the ciphertext messages in such a way that their XOR remains the same. Therefore, the tag remains the same, but it's a different message. So let me motivate the definition of symbolic authenticity using the example that I showed you on the previous slide. So the key is that we define symbolic authenticity in terms of a unification problem. So here's a unification problem where on the right-hand side, we have the tag of a valid message. And on the left-hand side, we have the tag of some message that the adversary tries to forge. So again, the capital C1, C2, and capital TK, those are all variables. So here, by solving this unification problem, we are asking the question, can the adversary modify the message somehow in such a way that the tag remains the same? Of course, this unification problem has a trivial solution. So what this trivial solution says is that if the adversary doesn't modify anything, then of course this unification problem is trivially solved. But that doesn't correspond to a new message. So we solve this unification problem, and we check if this trivial solution is the only solution to this unification problem. If that's the case, then authenticity is satisfied. Otherwise, authenticity is violated. So that's the key idea behind symbolic authenticity. So for this particular example, we can solve this unification problem very easily using the standard decompose rule and the standard variable elimination rule. And what we get is this unification, but it's not the trivial unification. So we know that in this case, authenticity is violated. But there are some complications to this problem. So first of all, the adversary are given multiple ciphertext messages, not just one. And then the adversary can choose plain text messages adaptively. So what that means is that the adversary sends the first plain text message and gets back the first ciphertext message. But now the adversary needs to send the second plain text message. Now the adversary can choose the second plain text message based on what it received. So what this means is that we should solve this unification problem modulo XOR and some other equations. So this unification problem says that on the left-hand side, again, we have the tag of some message that the adversary tries to forge. But on the right-hand side, we have this matter substitution omega IL. So intuitively, omega IL corresponds to the ICE ciphertext message that the adversary receives from the oracle. And it's a matter substitution. It can be instantiated by instantiating I and L, where L denotes the length of the message. So in this case, the length of the message is 2, so L is instantiated by 2. And so on the right-hand side, we have the tag of the ICE ciphertext message that the adversary received from the oracle. So what's the background equation? So suppose that there are 2 rounds of interaction between the oracle and the adversary, and suppose the adversary chooses the second message in this particular way. The details doesn't matter, but the point is we have 3 sets of equations where E XOR denotes the theory of XOR, and E1 captures the fact that all the ciphertext messages that the adversary received are all valid. And E2 captures the fact that the adversary can choose the plain text messages adaptively. So what's important is that E1 and E2 satisfy some certain properties, which we call the validity property, the stability, and the consistency property. So the validity property says that all of the messages that the adversary received are valid. And the stability property says that all the unrooted terms are irreducible in our theory. And the consistency property says that if we have 2 E-rooted terms or D-rooted terms, if they agree on their first arguments, meaning that they agree on the tweaks, they must also agree on the second arguments, meaning that we can only process a single message using a single tweak. So that's the basic property of a tweakable block cipher. So now I'm gonna talk about the definition of symbolic authenticity. It's a bit technical and it depends on other definitions. So I'm gonna introduce the definition of symbolic authenticity and, just to give you a high-level idea, and then I'm gonna introduce the other definitions that symbolic authenticity depends on. So essentially, we solve a unification problem, right? We try to unify the tag of the message that the adversary tries to forge and the tag of the ICE ciphertext message that the adversary received, and check if the trivial solution is the only solution. So that's the overall idea. And we do so modulo a theory which we call an AE theory. We are only interested in some particular unifiers called XOR EV unifier, which is the unifier modulo the AE theory. So what is an AE theory? AE theory is essentially a theory that satisfies the three properties: validity, stability, and consistency. So in our previous example, E1 unit E2 is an example of an AE theory. And then we have a definition of a computable substitution. So a substitution is computable if it maps each variable to the XOR of constants and variables. So as an example, if C1 maps to C2 XORed with those two constants, that's a computable substitution because the adversary knows all of the terms and therefore can compute this XOR. But if we map C1 to this E-rooted term, then that's not a computable substitution because the adversary doesn't have the key, therefore cannot do the encryption. So that's not computable.
Sorry to interrupt you. You have to conclude in 2 minutes.
Okay.
Sorry for that.
Sorry. So the basic idea is that we solve some unification problem, and we do so modulo an AE theory, which is a theory that satisfies three properties: validity, consistency, and stability. And we only check some certain unifiers, which we call XOR EV unifier. So if we go back to our previous example, so we can solve this unification problem, again, modulo the AE theory, and we can solve this unification problem in a straightforward way using standard inference rules. And the key is that we can use the variable elimination rule as long as it produces a computable substitution. So as another example, if we consider this particular authenticated encryption scheme, it satisfies symbolic authenticity. So the details are not that important, but an important point is that so we solve this unification problem. Along the way, we get an equation, but we can't use the variable elimination rule here because it doesn't give us a computable substitution. So what we do instead is that we apply this other rule called split to proceed. So those are the inference rules. So we have the standard decompose rule, and decompose n is an optimization rule. We have a restricted form of variable elimination rule. So the point is that those two restricted forms of the variable elimination rule give us computable substitution. So this is the split rule that allows us to proceed if we get stuck and can't get a computable substitution. So those are all the rules, and so in the algorithm we just solve an unification problem, and we check if we can only get the trivial solution. If so, then authenticity is satisfied. Otherwise, authenticity is not satisfied. So to conclude, we give an inference system for checking symbolic authenticity. We find all the special unifiers and check if we only get the trivial one. And the inference system is sound, complete, and terminating for checking symbolic authenticity. So that's the end of my talk. Thank you very much. Are there any questions?
You have to unmute yourself, Christopher.
Yeah, thanks a lot for this nice talk. And so if you have questions, don't hesitate to use the chat or to raise your hand. I don't see any questions so far. So I have a question. I think that in your example, all the message forged by the adversary corresponds to a ground term. Does it mean that in fact you are solving a matching problem instead of a unification problem, in the sense that one side of the equation is always ground?
That's a good point. Yeah, I think so. So one side of the equation is always ground. So that's a matching problem.
So you are always, in fact, trying to solve a matching problem, modulo, let's say, some equational theory plus the XOR operation.
Yes, that's correct. So we solve the matching problem, the modulo.
And how do you take into account the additional axioms corresponding to the theory EV? How do you take these axioms into account in your unification procedure?
So in a unification procedure, essentially we just have the standard decomposition rule. We have restricted form of variable elimination rule, and we have a split rule. So essentially, the split rule depends heavily on the properties yeah.
So the split rule does not correspond to a decomposition.
Oh, I'm sorry.
Does the split rule correspond to a decomposition, a classical decomposition? Because
the split rule doesn't correspond to the decomposition rule directly. But I would say they are related.
Because I had the impression that all the rules you used was very similar to a decomposition. When you see the split rule here, it looks like a decomposition, isn't it?
Yes, it looks like decomposition, but there are some constraints. Like so, on both sides, you need to have a pair of E-rooted terms or a pair of D-rooted terms.
Okay, so you have side conditions.
Yes.
Okay, I see. Corresponding to the definition of EV theory, or I don't remember the name you used for the, or A theory, like the unicity property or stability, I think. Yeah, it was stability. If you go back to the definition. Yeah. Validity stability. Could you expand this definition? Do you have an expansion of this definition? Or showing how do you define validity, stability, and consistency? Do you have?
Yes. So
Okay, I see.
Yes.
Now I see. Okay, and do you use the same definitions for a computable substitution as in the previous talk, or
no,
is it something new?
It's something different. So
okay.
Yeah.
So the notion of computable substitution does not correspond, as previously, to a way to take into account the history of because in the previous talk you defined a notion of computable substitution taking into account the history of how you compute the different messages.
So in the previous talk, computable substitution means that you map each variable to the XOR of some previous terms, because things happen in some certain order, and you need to take into account that order. But here, you sort of assume that you have the adversary have this interaction with this oracle. And after all of the interactions, now the adversary has everything, and now the adversary tries to forge a new message.
Okay.
So here, computable substitution just means each variable is mapped to the XOR of something that the adversary already received.
Okay.
Yeah.
Okay, I see. So could we say that it's a special case as compared to the previous definition, or is it, let's say, completely independent?
That's a good question. I think it could be considered as a special case.
Okay.
Yeah.
I see. So other questions I see in the chat. Yeah, no, it was just a comment about the possibility to continue the discussion. I think we can continue the discussion. Also due to the fact that the next session will start not directly. So are there other questions before we stop the session? No? Okay, so thanks again.
Thank you
for this very nice talk.
So we will now have a break, right?
Yeah, I think so.
For half an hour. So we